Hello and welcome to this FMSP online revision session. This session is looking at the MEI Further Pure 1 specification and the topic of matrices. We'll start by looking at the specification. There seems to be an awful lot for this topic, but some of it is just summarising the mechanics of manipulating matrices. Point 1 is exactly one of those. When it talks about conformable, that just means that it matches up properly so that you can multiply them. You need to know the zero and identity matrices. So the identity matrix is where you've got ones in the leading diagonal and zeros everywhere else. Any size of square matrix. Equal matrices, well, those are just matrices which are identical. Remember that matrix multiplication is associative, so keeping the order that you write them the same, but working out BC first and then pre-multiplying by A, or working out AB first and then post-multiplying by C doesn't make any difference. But if you actually swap round the way you write your matrices, then they will not be equal in general. The matrices associated with transformations, we're going to look at these 3 points in some detail. Then we've got the determinant and inverses of matrices. Make sure you learn how to find the determinant and know that it gives the area scale factor. That often comes up and it's an easy mark. You need to understand what is meant by an inverse matrix and be able to find them. And the product rule for inverse matrices, that's knowing that the inverse of AB is the inverse of B multiplied by the inverse of A. We'll have a look at an example of using matrices to solve linear equations, and also how to interpret those where you've got a singular matrix where its determinant is 0. So let's have a look at the key points you need to know. The inverse of a general 2x2 matrix. AD minus BC is called the determinant of the matrix. And note that the determinant is just the denominator. The determinant is not this expression here. Okay. You multiply your matrix by 1 over the determinant to find the inverse. If the determinant is 0, the matrix has no inverse. And if we're looking at a system of equations, then you've either got no solution or infinitely many solutions. In terms of the 2x2 matrices that we're looking at in Further Pure 1, if you're looking at those geometrically, then either the lines are parallel, so you've got no solution, or in fact your two equations actually represent the same line and you've got infinitely many solutions. Looking at transformation matrices, the easiest way to do this is to consider what happens to the point 1, 0 and 0, 1 under the transformation. So an example, if we look at reflection in the x-axis, then the point 1, 0 maps onto itself, and the point 0, 1 maps down to the point 0, minus 1. And you put those two together to form your new equation. It isn't worth learning these. It's much easier and safer to quickly work them out in the exam. For rotations, however, it is worth learning the general anticlockwise rotation because that's fiddly to work out. Remember, when you are combining transformations, if T is followed by S, then the matrix is ST and not TS. It goes the other way round. You apply T first and then S. If xy is an invariant point, that means it doesn't move, and when you multiply the matrix by it, it doesn't change. You might have an invariant line, and that could be made up of invariant points, or it might be that the points move to other points but stay on the line. Let's have a look at some questions. We've got a matrix, we've got a transformation applied to a figure of area 3 square units, and we've got to find the area of the transformed figure. So that's going to be using the determinant. Find M1 and the determinant of M inverse and the determinant of M inverse, and explain the significance in terms of transformations. Okay. So for part 1, the first thing we need to do is to find the determinant of M, and that is 12 take away 0, which is 12. And that means that the new area is going to be 12 times 3, which is 36 square units. For part 2, the inverse matrix, we've already found the determinant, it's 12, so we multiply by 1/12, and we swap A and D, and we change the sign of B and C. The determinant of M inverse is 3/12 times 4/12, take away 0, which is 1/12. For part 3, det M times det M inverse is 12 times 1/12, which is 1. And it says explain it in terms of transformations. So M inverse followed by M is the identity transformation. So the area wouldn't change. Scale factor 1. Okay, let's see how the mark scheme applies to this question. For part 1, there is a method mark for finding the determinant and multiplying, and an accuracy mark for doing that correctly. For part 2, there's a method mark for attempting to find the inverse and an accuracy mark for doing it correctly, and there's just a single mark for finding the determinant of the inverse. For part 3, there's a mark for showing that the product is 1, and then there's an explanation mark for justifying that in terms of transformations. Okay, we've got several questions to look at because there are a number of different points that we need to cover. So here we've got 3x3 matrices. The first thing is show that, so we need to make sure that we've got enough working. And then state the value of A for which A inverse doesn't exist, and write down that inverse. Now then, it's a 3x3 matrix, but it will be easy. Okay, and the clue is in this first bit, that AB is a multiple of the identity. Then it says use A inverse to solve those simultaneous equations, so we have to use that method. And notice that the coefficients on the left hand side are that matrix with A equaling 4. And then what can you say about the solutions here where A is -8, and the suspicion is that that's going to be the one where we have a problem in part 2. Okay, let's get going. So part 1, AB equals -2, 3, 1, 1A minus 1, minus 5, 1, 2, 2A plus 1, minus 5, minus 3 minus A, 3, 1, minus 1, 1 plus 5a minus 13 minus 2 minus 3a. So they're making quite certain that you're not going to be able to use a calculator to do this multiplication. Okay, so we get minus 4a minus 2 minus 5 plus 15 plus 5a. The next line is all numbers and it comes to 0. And then we get minus 2 minus 10a minus 13 plus 10a plus 15. For the next line we get 6a plus 3 minus 5a minus 3 minus a, and then in the middle 9 plus a minus 1, and then 3 plus 15a minus 13a minus 2a minus 3, and then the last line 2a plus 1 plus 5 minus 6 minus 2a, and then it's all numbers again and it comes to 0, and finally 1 plus 5a plus 13 minus 4a minus 6. It's important that you have all of that working in because it's a show that question. And then you see that the first term simplifies down to 8 plus a. Then we've got 0. Then the top right all cancels, that's 0. And 0. And in the middle we've got 8 plus a. And we get 0, 0, 0 and 8 plus a. And that equals 8 plus a multiplied by 1, 0, 0, 0, 1, 0, 0, 0, 1, which is 8 plus a I as required. Now then, that means that b is more or less the inverse of a. We're going to be able to find the inverse of a just by dividing b by 8 plus a. And that means that the inverse won't exist when 8 plus a is 0. So a inverse does not exist when a is minus 8, and a inverse is 1 over 8 plus a, and then the matrix B, 2a plus 1, 3, 1 plus 5a, minus 5, 1, minus 13, minus 3 minus a, minus 1, and minus 2a minus 3. And that's as hard as finding the inverse of 3 by 3 matrix gets in Further Pure 1. You'll learn how to do it properly in Further Pure 2, but in FP1 they will practically give you the inverse, and you'll just need to do a little bit of tweaking so that when you multiply them together you do get exactly the identity. For part 3 we've got to use A to solve the simultaneous equations. Well, what we've got there is with a equaling small a equaling 4, we've got our matrix A times xyz equaling minus 55 minus 9 minus 26, and therefore xyz equals A inverse, which we've just worked out. I'm just going to write B up here actually. 2a plus 1, 3, 1 plus 5a, minus 5, 1, minus 13, minus 3 minus a, minus 1, minus 2 minus 8 minus 3, sorry, minus 2a minus 3. And then I'm just going to plug in a equals 4 into that, so that will be 8, 9, the plus 1/12 at the front, so that's 9, 3, 5a is 20, so that's 21, minus 5, 1, minus 13, minus 3 minus 4 is minus 7, minus 1, and minus 8 minus 3 is minus 11. Multiply that lot by minus 55, minus 9, minus 26. Grab a calculator, and you could, if you've got the matrix function on your calculator, plug that in to do it, or just do 9 times minus 55 minus 3 times 9 plus 21 times 26 and get your answer that way. So 24 minus 72, 108. And conveniently, all those numbers divide by 12, get 2 minus 6, 9. It's important then to write down your solution. X equals 2, y equals minus 6, z equals 9. For part 4, we've basically got the situation where a equals 8. There is no unique solution. And the fact that this part of the question is only worth 1 mark makes it clear that you're not expected to work out whether there are infinitely many solutions or no solutions. Much too much work involved there. It's just 1 mark. You're just supposed to observe that there is no unique solution. So let's have a look and see how the mark scheme works for this long question. So there is M1 for an attempt at AB, and that means at least 2 of the terms in the leading diagonal and 1 other, and an accuracy mark for getting that final simplified version, and another mark for then writing it as 8 plus a times I. There's a single mark for observing that a can't be equal to minus 8. And there's a method mark for taking the matrix B and multiplying it by 1 over something which is not 0, which is not 1. And there's an accuracy mark for having that fully correct. For part 3, there's a mark for plugging 4 into the matrix B. There's a method mark for correctly attempting to use the inverse matrix, and then there are 3 answer marks for getting the correct 3 answers. And for part 4, there is just 1 mark for stating that there is no unique solution. Okay, and 2 more questions, one on transformations. So this is question 1, so it's likely to be straightforward, and you can see write down. Then it's find the matrix of the rotation followed by the reflection, and then asks you for a single transformation that's equivalent to both of those. So you might have memorised these, but it's very quick to work them out, and that saves you trying to memorise a whole load of very similar looking matrices. So the point 1, 0 rotates round to the point 0, 1, and the point 0, 1 rotates round to the point minus 1, 0. So we combine those 2 into the matrix 0, 1, minus 1, 0. So that goes to there, and that is the right hand column. We do a similar idea for the reflection in the line. Whoa, sorry, difficult drawing straight lines on here. That's a straight line. Reflection in the line y equals x, and basically our 2 points swap places. So 1, 0 goes to 0, 1, and 0, 1 goes to 1, 0, and that gives us the matrix 0, 1, 1, 0. For part 3, we need to get these in the correct order. It's rotation, then reflection. So my rotation matrix was 0, 1, minus 1, 0, and the reflection comes after that, so I need to put the matrix before and work that out, and it comes to 1, 0, 0, minus 1. And for part 4, I simply need to work out what's happening with that matrix. Well, the point 1, 0 goes to the point 1, 0, so that stays put, and the point 0, 1 goes to the point 0, minus 1, so that is a reflection in the x-axis. So let's have a look at the mark scheme for this question. For part 1, there was just a single mark. For part 2, just a single mark. You could learn those. For part 3, there is a method mark for the correct order, following through from what you had in parts 1 and 2, and an accuracy mark for getting the correct answer. And for part 4, there is just one single mark for getting that correct answer. There's no follow through there because you could work that out from geometrically from the transformations, and doing that can be quite a useful check to make sure that you've got the composite matrix correct. Okay, and this is our final question on simultaneous equations. Simultaneous equations represented by that matrix equation. Write down the matrix M. State the value of k for which M inverse doesn't exist. That will be looking at the determinant. And then find M inverse in terms of k when it does exist. Then it says use M inverse to solve the simultaneous equation, so we have to use that method. What can you say about the solutions of the equations when k is that? That's probably then the value for which that we need up here. Two equations be represented as two lines. Describe the relationship between these two lines in these various cases. So we're going to have this one, which turns out to be part B. Okay, same values there. And here we've got this situation with k being minus 3 over 2. So probably one of them is going to turn out to be parallel, and one of them is going to turn out to be identical. Okay, let's start solving these. So first of all, write down the matrix M. That's 2, 3, minus 1, y. So state the value of k for which that doesn't exist. So I need the determinant of M. That's 2y. Sorry, I put y and I meant k, didn't I? That should be k, ky. So the determinant is 2k plus 3. The problem is when that equals 0, implies k equals minus 3 over 2, as we suspected. Find M inverse in terms of k when it exists, so that is 1 over 2k plus 3. And swap a and d, so that will give me k and 2, and swap the signs of the other two terms, 1 and minus 3. Then it says use M inverse to solve the equations. So we've got mxy equals 1 21 implies that xy is the inverse, so k is 5, so that's 1/13. 5, 1 minus 3, 2 times 1/21. That's 1/13 of 26/39, which is 2, 3. So our solution is x equals 2, y equals 3. What can you say about the solutions when k is minus 3 over 2? There are no unique solutions. And then for part 4, A, we know that the lines intersect because we've already dealt with it. For part B, let's have a look at what it looks like. So we've got 2x minus y equals 1, and 3x minus 3 over 2y also equals 1. That's 2x minus y equals 1, and if I multiply the second equation by 2, I get 6x minus 3y equals 2. Which would then give us, dividing by 3, 2x minus y equals 2/3. So the lines are parallel. For part C, we've got 2x minus y equals 1 and 3x minus 3 over 2y equals 3 over 2. And that gives us 2x minus y equals 1. And multiplying the second equation by 2 again, 6x minus 3y equals 3. And you can see that those are in fact the same equation, and so we say that the lines are coincident. They coincide with each other. Okay, let's go back and see how the mark scheme works for this final question. Write down the matrix M. It's 2 marks and it's -1 for each error. For part 2, there's a method mark for observing that you need 2k plus 3 equaling 0, and an accuracy mark for getting k equals minus 3 over 2. For finding the inverse, there's then just a single mark, because of course you've already found the determinant. And then there's a method mark and an accuracy mark for writing down the correct equation to solve there, and an accuracy mark for getting out the correct solution. For part 3, there is just 1 mark for observing that there are no unique solutions. For part 4a, there is 1 mark for observing that the lines intersect, because you've already done the work for that. For part 2, 1 mark for observing that they are parallel, and part 3, 1 mark for observing that they are coincident. Well, there's quite a lot of material in matrices, but that is all you need to know for this topic. I look forward to your company in the rest of the MEI FP1 videos and wish you all the best in your exams. Goodbye.